complex cobordism 2 category and its central extensions.
Thank you very much, Oscar. Thank you to the organizers for inviting me to this very stimulating conference, which I have enjoyed immensely, and for the opportunity to give a talk. Today I'll tell you about the complex cobordism 2 category, also known as the art of taking Riemann surfaces and chopping them into pieces. And I drew some two morphisms just to give you a preview of the kind of things that we're going to be talking about. But let me start by telling you about the usual one category of complex cobordisms, where we only have circles or disjoint unions of circles as incoming and outgoing manifolds, just a little bit simpler. So, definition, and maybe I should really write preliminary definition because it's going to just be exactly the kind of things that I don't want to focus on. Complex cobordism is well, you'll have this picture in mind of like a bunch of circles and like a bunch of genus in the middle. I'm going to view these things as ringed spaces. Just that's one of the possible ways of talking about a complex structure. It's a ringed space. Locally isomorphic to, well, if there was no boundary, it would be locally isomorphic to the complex plane with its sheaf of holomorphic functions. And given that I do want to allow boundary, I'm going to talk about the upper half plane. And then, of course, there's also plus a decomposition of the boundary into in and out. That's the usual thing you expect. Here I told you what sheaf I put on the complex plane. I should tell you what sheaf I put on the upper half plane. So I'm going to give two equivalent definitions of this sheaf, and I'm going to phrase the equivalence between those two definitions as a technical lemma. For U, an open subset of the complex plane, and F, a function defined on U intersect H. The following are equivalent. One, F is continuous. Smooth when restricted to the boundary. And of course, holomorphic on the interior. Okay? And the second equivalent characterization is there exists a function f hat decide on all of u, which is smooth, again, holomorphic on the interior.
U is open.
U is open, yes. And the restriction of f hat to u intersect h is the function f we care about. So this technical lemma is an indication that this notion is a good notion, because those two characterizations look like they maybe aren't the same, but actually they are the same. So it's enough to be continuous and smooth on the boundary in order to be the restriction of a smooth function everywhere. Okay, so that's a sheaf I put on the upper half plane, and therefore that completes that definition.
Could you just as well do it holomorphic on U rather than U intersect?
That would be different. So you're asking for the existence of an analytic continuation a bit beyond the boundary. And that in particular implies that restriction of f to the boundary is real analytic, whereas this condition only implies that the restriction to the boundary is C infinity. And that's a very good question. Why not look at what you're suggesting, which is also called the restriction of the sheaf of analytic functions, right? We have a sheaf here. We can restrict that sheaf to this closed subspace. There's a well-defined notion of restricting sheaves, and the sheaf that I'm naming is not the restriction. That's the sheaf that you're naming. So why this choice? So if you think about it, putting the sheaf of analytic functions that extend a tiny bit beyond the boundary is really the same as looking at complex cobordisms with a little color whose size is not determined, but essentially you should think of that size of the color as being however far you can analytically continue your charts. Then, of course, that also encodes the fact that the inclusion of the boundary, let me call this thing sigma, the inclusion of the boundary into sigma is real analytic. So why not this? Well, if you think about the kind of pictures that I want to get at the end, in particular, if you look at this one, there's a feature which I'm going to redraw here just to emphasize it. I have a yellow line that agrees with the red line for a certain part of it and then diverges. And if I want to have identities, that's an identity, and I want to be able to glue horizontally a two-morphism with another two-morphism, I will get things like that. So it is not an option to disallow this. And that cannot be achieved with analytically embedded one-manifolds. That's just like the thing that analytic continuation tells you cannot happen. And therefore, I don't want a definition that forces my one-manifolds to be analytically embedded. And I don't want that. And I'm going to use this instead for that purpose. So I haven't yet allowed pictures like that in this definition, and so I still need to work on it. But let me first tell you about composition of cobordisms. Also known as conformal welding. This is not a term that I invented. This is a classical notion. So we have a one manifold. Here, let me stick to my color coding. I have a one manifold. Here, S is going to be my letter for the one manifold, and then we have inclusions into, let's see,
Andre, in your technical lemma,
yes,
you assume that F is globally C0 but not C1. Is that right?
I assume that it is continuous, meaning C0.
No, but that's on U intersects the boundary, but the original function F, shouldn't you assume that's continuous to begin with?
F is continuous. F is the function.
Great, okay. If it's continuous, comma, it's smooth on the boundary.
F is continuous. The restriction of F to the boundary is smooth.
Thank you, great.
The restriction of F to the interior is holomorphic.
Oh, by the way, are you using these F's to make sense of ring space in the definition? Or are we supposed to understand that?
Yes, I'm equipping the upper half plane with the sheaf that assigns to every open U, and to every open U intersect H, the set of functions that satisfy those equivalent conditions. Yes. So this technical lemma is part of this definition. Great. So I have this situation, and I want to build, well, the obvious thing. And having set up definitions in this particular way makes this composition of, this is a smooth embedding, and that's a smooth embedding. Having set up definitions that particular way makes it easy to define composition. It is the push out in the category of ringed spaces.
Does that surface at the bottom have genus 3 or 4?
Sorry?
The surface at the bottom of your picture, does it have genus 3 or 4? Or to put it another way, is that thing in the middle another hole, or is it a curve, the image of the surface?
Yes, the thing in the middle is the image of S,
Okay.
which I decided to draw because then I can make a statement about it, which is that it's going to be smoothly embedded in the ambient thing. Not analytically, smoothly. So, yeah. And here's a proposition. Which appears in, I think the earliest reference I know is an unpublished little manuscript by Graham Siegel, but you can also find it on Wikipedia, an actual proof. Of a special case when these are two disks. Just look for conformal welding, which says that if, let's say this is sigma 1 and this is sigma 2, it says that this is a complex cobordism. As defined there. So really, if you think about it, that ring space, which I so clumsily drew up there in the bottom, that's a space that knows what it means for a function on it to be continuous, smooth on the whole thing. Sorry. Let's focus on this one as opposed to that. It knows what it means to be continuous, smooth on the image of S, holomorphic on one side and holomorphic on the other side. That's the type of functions that it knows. And it's a lemma that in the complex plane, if I draw a curve and I draw an open, and I take a function which is continuous on this open, holomorphic outside of the curve, and actually you don't even need to say it, smooth on the curve, but that's actually a consequence. So continuous and holomorphic outside from the curve, it automatically is holomorphic everywhere. That's a lemma from complex analysis, which is not very hard. It's a bit similar to if you have a function which is holomorphic everywhere and everywhere but a point and is continuous at that point, that it's actually holomorphic everywhere. And so that's the underlying lemma that you should keep in mind when interpreting this. Like, I'm giving you a set of functions that looks like maybe it's not the holomorphic functions, but actually it is holomorphic functions for a unique holomorphic structure on this glued topological space. Great. So that's how much I want to say about the one category. Let me now go on to the two category. So I need to tell you about two morphisms, which are going to look like those pictures I drew over there at the very far right. And just like in this definition, I just need to give you some local models. I just need to tell you it's going to be a ring space that looks locally like either this or that or that. And if you think about the local models, we have all the local models. The only one that we're missing is this one. And what is that? That is the stuff that's between the graphs of two smooth functions. So take a smooth function from R to R, another smooth function from R to R, one which is bigger than the other, or bigger or equal, and then just look at the stuff in between. So that's going to be our local model. For the two morphisms. So pick F and G from R to R, and I'm going to pick them to be smooth functions, C infinity functions, and I'm also going to assume that F is smaller or equal to G. Now I'm going to draw the graph of F and the graph of G. So here's y equals g of x, and this is y equals f of x, and I care about the stuff in between. So let me write x sub fg to be the set of points x plus iy in the complex plane, such that well, the obvious thing, f of x smaller or equal to y smaller or equal to g of x. Essentially this space in between. And then there's also a variant when I'm around here, and that's the place where the one manifolds stop. So I need the same thing where I replace this r by r plus. So That's one type of local model, and then the other type of local model is f smaller than g. Now this is R plus, and let me be specific, bigger equal 0 to R smooth. There's going to be an extra condition, which is that all the derivatives of f at 0 agree with all the derivatives of g at 0. Right? If I have one of these things, I need to be able to glue these things together. I need to know what the derivatives are on one side in order to be able to glue, so that wouldn't work if I don't impose this condition. And then you have essentially the same picture, except now things stop here, like stopping point. And you have the analogous definition there, where now you add the condition that x is positive or non-negative. So now there's a technical lemma that says that the technical lemma holds for those types of spaces. So let me say it in words. I won't write it down because it's essentially written there. It says that, so what I'm doing is I'm replacing H in the statement of this technical lemma by this closed subspace, or the corresponding closed subspace where I also include x bigger than 0, if I'm in that case. It says that for U in C open and for f, a function defined on U intersect x, to C, the following are equivalent. 1, f is continuous, and its restriction to the graph of f and its restriction to the graph of g are smooth. So these are now smooth, like the yellow curve and the red curve. So those restrictions to these graphs should be smooth. And it's holomorphic on the interior being this possibly disconnected region that you have in there. That interior could well have countably many connected components. That's something that can happen. I'm not bothered by that. So that's condition 1 is equivalent to condition 2, which is there exists a smooth function defined on the whole open of the complex plane, holomorphic on the interior, and whose restriction is the given function. Great. So I've said it in words. I don't need to write it down. There exists a good notion of holomorphic / smooth function on these things. And I say holomorphic / smooth because when restricted to the interior, it becomes the notion of holomorphic function. But when restricted to the part where the two things are touching each other, it becomes the notion of a smooth function. So it's smooth here and it's holomorphic there. It interpolates the two notions. Great. So I can now tell you what the complex cobordism 2 category is. The only thing that I really haven't told you about is what are the objects. And you might think the objects are just points. Well, they're not quite points. They're the kind of points where if I need to identify derivatives at this side and at that side in order to be able to glue to infinite order. So they're going to, again, be ringed spaces, but they're going to be ringed spaces that, yes, they have just one point, but the ring is going to be have more information. Okay, so let me make some space. Oh, look at that. You can keep this, that says the complex cobordism 2 category, and keep a definition symbol up there. So, the objects are going to be ringed spaces which are isomorphic to finite disjoint unions of the following. A point, and my ring is given, my sheaf of rings, which is just a single ring in this particular case, the field of formal power series.
Did you say finite disjoint unions?
Yes. Yes. No, I didn't. Did I say it?
You did say it.
I did say it. Thank you. Good. I definitely meant it.
Well, you also said a field of formal power series.
Let me emphasize compact. Ringed spaces, locally isomorphic to, well, either the real line with its sheaf of smooth functions, or the positive real line with, again, its sheaf of smooth functions. And you might think, does it mean to be a smooth function on the positive real line including 0? Well, there's equivalent definitions. One of them is a function that happens to be the restriction of a smooth function defined on the whole real line. That's an okay thing to say. Or like a little bit further from 0. And then two morphisms. Are going to be compact ringed spaces, locally isomorphic to well, locally isomorphic to one of these. Either to this or to that.
So do you need, isn't the first type of local model a special case of the second type?
Yes, it is. Yeah. So just like here, I didn't say R or R plus, because actually R is a subspace of R plus. You can actually do the same thing here, yes. So, all compositions are given by push-outs in the category of ringed spaces. And yeah, it's a theorem that this is closed under such push-outs. Not quite obvious. So if you think a bit about it, already in the case of one manifold, I have a one manifold that ends and an inclusion of ringed spaces of one of these power series rings into like the end point, and then like another one manifold, and then you do the push out in the category of ring spaces. Well, the resulting thing, obviously topologically, is a one manifold, but it really, what it has is a notion of smooth functions from one side and smooth functions from the other side, with conditions on each individual derivative that the derivatives agree. And well, okay, if you know what it means to be smooth, like if it agrees on all derivatives, then it is smooth. Yeah, for these types of things, taking two of these and gluing them together, there's something to be proven, namely you need to construct new functions f and g such that it's again one of these models and show that these functions are smooth. And so, okay, so that's a thing that that is true, and yeah, so I've checked that. And so you get a two category, or rather a bicategory of these things. Yes?
Might be a bit annoying, but firstly, do you not get problems if you have a power series that has no convergence radius?
No, you don't get problem.
And second, do you want to formally add identity one morphisms? Or do you just not care about them?
Do I want to formally add identity one morphisms? Yes, I do. So I got it wrong. Great. Yeah, okay. Thank you. I want to also allow as one morphisms ring spaces that are isomorphic to the things on the top, and then disjointures of these. Sorry. Indeed. Yeah, so as far as radius of convergence is concerned, you should think of a generic C-infinity function as having everywhere zero radius of convergence of its Taylor series. That's the generic behavior of a C-infinity function. If you're used to thinking about C-infinity functions that have positive radius of convergence of their, I mean, this is, like, you're not thinking about C-infinity functions, you're thinking about some other types of functions. Like C-infinity typically don't have radius of convergence that's positive. Anyways. Okay, so now there's the question, which is, why didn't I do the thing that always works? Namely, there's a thing that always works in all dimensions, works with any geometry, which is to declare the objects, in this particular case points, to be points with a little germ of, in this case, two-manifold, with a complex structure in it. And why did I not take the one morphisms to be one manifold with a little germ of two manifold around them? So if you do that, well, I said you shouldn't take the one manifold to be embedded in the real analytic way. I explained why that. But let's say we don't. Let's say we put them to be embedded in a smooth way. Then why not do that? And the reason is that I want the set of one morphisms to have an easy classification. So let's think about a circle. If I have a circle, just a smooth circle, up to isomorphism, there's only one of them. Okay. Now let's take my circle and embed it inside a little piece of Riemann surface, a germ of Riemann surface. If I insist that this embedding is real analytic, then again there's only one circle up to isomorphism. And that's okay, but it doesn't work for my purposes because I want these things that sort of like are together and then diverge. So let's say we don't insist that the circle is embedded in a real analytic way. We say it's embedded in a C-infinity way. Well, suddenly there's many circles that are not isomorphic. For example, there's the one given by a real analytic embedding, and then given another circle, there's, I don't know, like all kinds of crazy invariants, such as the set of points, such as the embedding, such as where the embedding is real analytic, and the set of points where the set of all derivatives has non-zero radius of convergence, and all kinds of stuff that. So there's many circles, and somehow that doesn't sound right. So. Well. Now, you might ask, why do I care if there's many circles? And the reason I care is that is conformal field theory. So I should have maybe advertised this thing earlier. My investigation of the complex cobordism 2 category is part of a wider project together with James Tenner, whose aim is, well, let me put his name, James Tenner. So with James Tenner, our aim is to construct chiral CFTs. I'm going to abbreviate that with chi CFT, chiral conformal field theories, in the axiomatic approach of Graham-Siegel, a la Siegel. And if you know a bit about chiral CFTs, there's only one thing that corresponds to the circle up to isomorphism. There's not just, there won't be as many different algebraic things as there are ways of embedding a circle in a C infinity way into something like into a Riemann surface.
Are you going to say what you mean by chiral?
Yeah.
Later.
It's now a question of time management. Sure. So, yeah, let me say that. Okay. So. So the first thing to know is that when people talk about conformal field theory, there's two things. There's chiral CFTs and there's full CFTs. And these things are just different things. It's a bit like Lie algebras versus associative algebras. They're both algebras, but they're just not the same thing. And I mean, there's functors between chiral CFTs and full CFTs, just like there are between Lie algebras and associative algebras, but they're just not the same thing. And if you try to put them in the same world, I mean, for example, I could talk about vector spaces equivalent to the binary operation that's neither associative nor Lie, and then Lie algebras and associative algebras are both examples of that, but in there they don't have any intersection. There's no such thing as a thing that's both a Lie algebra and both an associative algebra. You can do the same thing with CFTs. You can put chiral CFTs and full CFTs inside a bigger world where they both make sense, and in that bigger world it is impossible to be both of these things, like they're just distinct notions. Maybe the trivial theory is a special case of both, but like that's the only one. So I'm talking about chiral CFTs because these are the ones that are that sort of come first in the order of, like, if you are trying to construct these things, you first try to construct the chiral CFTs and then construct the other ones.
Andre?
Yes?
Do your morphisms have a topology? Are they spaces? Or are they just sets?
Well, they definitely are sets. They're also spaces. They also have the structure of closed subspace of a topological vector space. So they behave a bit like manifolds with boundary in infinite dimensions. Manifolds maybe with corners would be more appropriate. So they're infinite dimensional, they're topologized, they have a notion of interior where they're manifolds, and they have a notion of boundary where they're not manifolds. So there's there's something to be said there. Okay, so let me just quickly tell you what a chiral conformal field theory is, because there was interest from the audience. A chiral CFT, and I'll give you is a symmetric monoidal functor from the conformal, that's, maybe I want to write here cob, and then here conf. So, okay, I'm doing the non-extended version here, so just one manifolds and two manifolds, into concrete linear categories. So maybe I spend one word to say what a concrete linear category is. A concrete linear category is a linear category equipped with a faithful functor to the category of, in this case, I guess, Hilbert spaces would be the relevant thing to say. So, examples of concrete linear categories are categories of representations of some algebra. It's like it's a linear category, and there's the notion of the underlying representation. So that's the forgetful functor which is always a faithful functor.
Need some continuity on such a functor? I mean, is it just a functor?
I have not finished the definition. Yes, you need something that controls things a bit. But let me first say that a concrete linear category is a category equipped with a faithful functor to Hilbert spaces and a morphism in concrete linear categories. If I have C1 and C2, it's going to be a functor plus a natural transformation. I'm going to call it Z. And then you can imagine how this becomes a category of these things. So for every one manifold, we have one of these. And for every complex cobordism, we have one of those. Now I'm going to address Nitu's question. You want, in addition to that, the assignment. So if I have a morphism sigma, then to it correspond two pieces of data, F sub sigma and Z sub sigma. Because, I mean, you get one of those that has an F and a Z. And I want F sub sigma, I want that to be locally constant. And I want sigma goes to Z sub sigma. So, okay, so once you know that the thing is locally constant, well, I'll just write it down. And I want this to be holomorphic. So there's a small lie here, which I will indicate by a little red exclamation mark. These are not, strictly speaking, locally constant. They're locally constant up to an anomaly. So, okay, like you if I projectivize everything, then yes, it's locally constant. Otherwise, it's not locally constant. And in order to make sense of that, well, you need to have a structure of complex manifold on the moduli space of all sigmas with fixed boundaries. So it's a bit tricky to say what this means. Like, this is a map from the moduli space of all cobordisms to the set of all, linear maps within Hilbert spaces, essentially. So you want that to be a holomorphic assignment. Great. So that's a chiral CFT. And just for the record, the full CFT, you would replace this by just a category of vector spaces, and you would drop the holomorphicity assumption. Okay. So maybe one thing that's worth saying is that this definition, even though very powerful, has turned out to be difficult to work with, meaning that even though it was formulated in essentially those terms by Graham Siegel in the late 80s, people have been unable to construct a meaningful collection of examples of things that satisfy these axioms. As far as I know, there's one construction in 2007 by Hessel-Postuma where he constructs something that one could call the free boson, and there's one construction in 2017 by James Tenner where he constructs something that is called the free fermion, and this is the entirety of all constructions so far of these things. But I should contrast this with the expectation. The expectation is that for every vertex algebra, there exists one of those. And so there is a huge gap between what is expected to be true and what has been constructed. And what James Tenner and I are in the process of doing is to actually provide large classes of examples of these things. But that's work in progress. So, I should talk about central extensions if I want to be, if I want to keep the title of my talk in mind. So, there are some partial constructions of these things where of some theories which are not the free fermion or the free boson, where people know what the category is that they want to assign to a circle, and people know what the functor is that you want to get, like from one of these to another one, but they know it in a way that doesn't quite produce the type of object that you want. In particular, if I take an object in here, so an object in here is going to be a Hilbert space. There's an underlying Hilbert space. It's a Hilbert space with extra structure. A Hilbert space with an algebra acting, typically, or maybe a group acting. You can, and you have a Riemann surface sigma. There's a procedure to produce a new vector space that wants to be the image under that. But this new vector space doesn't come in any obvious way with a Hilbert space structure, and so the procedure is there, but it lands outside of the, like you define a category, you don't say all representations, you put some adjectives. You say I want representations on Hilbert spaces, and then you put some more adjectives to sort of make things manageable, and then you have a construction that produces something where you can't check that what you get satisfies the desiderata. And actually, really what you get isn't a Hilbert space. What you want is to find on it an inner product and make it into a Hilbert space by completing with respect to the inner product. And that has turned out to be, well, it's a thing that Graham Siegel expected to be possible, and well, it wasn't easy to make it happen. And one of the things that James and I found in our project is that actually there is a new type of anomaly, which, as far as I know, had not been noticed before, that prevents this program from working in the way expected by people, but also tells you exactly what how things should go. And so, if I can find the eraser, then I will be able to explain. So, for every two morphism sigma, so one of these, there is an R. So the multiplicative group of positive real numbers, let me call that R plus. So there's a torsor for that group, which is associated to sigma. Let me call it D sub sigma. And so if I fix a cobordism sigma, then which could be like this, or could be actually like one of the things with cusps, but let me focus on that for the moment. If I fix sigma, then I have a corresponding, well, or one expects to have a corresponding F sigma and Z sigma. The CFT should provide such a thing. So I'm putting myself in this mindset of trying to construct one of these things. Well, what do? I take an object in here. I'm going to call it H, because after all, it's a Hilbert space with extra data. And I'm trying to construct F sigma of H. And as I told you, F sigma of H is a thing that people can write down, but isn't quite a Hilbert space. So it's a vector space. So you get a vector space. And you're sort of trying to make it into a Hilbert space. So if it was a Hilbert space, one of the things that it would have is an inner product, but equivalently I can think of the norm. So you would have a norm that goes from this to the positive reals. And that's the thing that people had a hard time constructing. And so the discovery is that this is not what you have. What you have instead is a well-defined norm landing in D sigma, I guess, union 0. So it's an R plus torsor, which is the recipient of, and if you trivialize this thing and choose any isomorphism with that, then it becomes a Hilbert space norm. Then it becomes something that comes from an inner product. So this thing is almost a Hilbert space. It's almost equipped to the data that you need to make it into a Hilbert space. It's equipped with an inner product well-defined up to rescaling, and that rescaling is governed by a certain thing which is canonically associated to any Riemann surface. So that sort of explains a little bit why this program of constructing these things has been encountering difficulties. It's because people have been trying to do something that actually cannot do. Like, there is no thing that you can write down. You need to first trivialize this thing in order to be able to. Okay, so let me tell you what D sigma is. Actually, to be completely correct, there's an invariant of the conformal field theory called the central charge, and we're talking about a certain power of this thing. Like, whatever the central charge is, you need to take a power of that. Okay, so let me tell you what this is. If sigma is a closed surface, this is the same thing as, so there's a thing that you can associate to every closed surface, which is called the determinant line. One of the possible ways of defining it is to say it's the top exterior power of H naught of the sheaf of holomorphic functions divided by or tensor the dual of the top exterior power of H1. That's one way of. It's a one-dimensional complex vector space canonically associated to every surface. Now I don't want a complex one-dimensional vector space. I want one of these. You take that vector space, remove the origin, and mod out by S1, and then you get the thing which is now just an R plus torsor. So that's what this is. If the surface has boundary, or even worse, if the surface has these kinds of features, then there is no determinant line which is defined, but that thing is still defined. So let me tell you what it is. So a point in this thing is represented by a Riemannian metric plus a number. The way you should think of it is every Riemannian metric gives an element of that torsor, namely that g comma 0 is an element. What's a Riemannian metric? Well, a Riemannian metric is really, I mean, have this picture here. Imagine something which is defined everywhere, and then I only keep the data along this piece of subspace. And so I need to put an equivalence relation because that's obviously too big as a set. How do I go from one Riemannian metric to another? I pick a function and I multiply g by e to the f. That's a way of going from any Riemannian metric to any other one. So e to the f times g, comma r, is declared to be the same as g, and then I need to take r times something. This is the multiplicative group of real numbers, so it's going to be r times something, and it's going to be r times e to the, and then something that I call s of e to the f g comma g. So now I need to tell you what that is. S of e to the f g comma g. That's a so-called Liouville action functional, and there's a version of that that includes boundary. I'll just write it down. It's the integral of, so everything is computed with respect to the Riemannian metric g. I have now a notion of size of the gradient. I have k is the scalar curvature of g, and then I also have a term that involves the geodesic curvature of the boundary, and that's called r. So k is the scalar curvature of the metric in the inside, r is the failure of the boundary being geodesic, and so that's just a formula, and that formula satisfies S of G1, G2 times S of G2, G3 equals S of G1, G3. And so the definition is well posed. That's just a computation which, if you're good with these things, you can do maybe in 10 minutes, and if you're me, it takes you 2 days to get it all right. But it works. I mean, I didn't invent these formulas, I just checked that they work. And also, there's the part of the picture where you might argue that the geodesic curvature is ill-defined. If like the thing is completely thin, I can embed it in lots of ways that have different curvatures. But this integral is over the whole boundary and needs to have a plus sign for the incoming boundary and a minus sign for the outgoing boundary, so that this ambiguity actually cancels out, drops out from the formula. I guess the next thing to say is that this assignment of sigma goes to d sigma is compatible with all types of composition. If I take a two-morphism and another one and I compose them vertically, the corresponding thing is the tensor product. If I take them and compose them horizontally, the corresponding thing is also the tensor product. And so what we get is something that one can reasonably call a central extension of the complex cobordism 2 category by the group R+. I would be very interested to compute the cohomology group in which this thing lives. And there's a sort of attempt computation where that seems to indicate that this group would be one-dimensional. This cohomology group would be one-dimensional, so that like this is really the generator. Well, I don't have, I haven't sorted that out yet. This is not at this point just a conjecture. Thank you.
Are there any questions or comments?
So your conclusion is that, so you hope that you can now build the examples from this twisted version?
Yes, so the situation is the following. Well, it's sort of like a bit tricky to say we can, given that we haven't written it up. But yeah, so James and I think that we can construct large classes of chiral conformal field theories. Associated to every chiral conformal field theory, there is going to be an element in this cohomology group. So a thing that assigns to every surface an R+ torsor, and which controls this stuff up there. What we don't know at present is that it is the expected multiple of the one constructed in this particular way. But we think it is, because we think that the cohomology group in which such things live is just one-dimensional, and we think that everything is just a multiple of this. So, yeah, that's the state of affairs.
So when you're in these constructions of these chiral CFTs, often you have this vector space, and then you want to sort of complete it to be a Hilbert space. And so if you had a norm, you could complete it, in the usual way. But now if you have, instead of a norm, this sort of d-valued norm, can you still complete those to be a
yes,
space?
Yes. One way of saying it is to say, trivialize this d, pick an identification with R, and then complete with respect to that, and then show that the completion is independent of the trivialization. Or you can phrase everything, like the whole theory, you just, every time you see R, you put this thing instead, and it actually works. You just need to know what it means for a thing to be a Cauchy sequence, and it means that you need to know what it means to tend to 0, and well, this is a thing that you can work with. So, yeah. So as far as finding a completion, you would get, the two things are equally good, one or the other.
Is there a relationship between the conformal class of G and the conformal structure on the surface?
Yes. Where G is a Riemannian metric in the conformal class of sigma. I didn't say it, but I should have said it.
Then, so then, in the case where sigma is closed, do you have a guess on on what d sigma is in the homology? You said you didn't know in general, but in the case where sigma is closed. You're saying for the particular CFTs coming out of the construction, or you're saying for
Can you specify your
D sigma
as defined here? Yes.
represents an element in the cohomology of sigma. I'm not thinking
No.
value then.
The thing that, so d sigma is a torsor. For every sigma you get d sigma. Now we have the assignment sigma goes to d sigma together with all kinds of compatibility with gluing, saying that if I have sigma 1 and sigma 2, then d of sigma 1 glued sigma 2 is that. So that whole package is an element in some H3 of the complex cobordism 2 category with coefficients in R plus.
So if you just restrict to the moduli space of, if you fix a genus and look at the closed surfaces of that genus.
Yes.
I was imagining you get an element in, I guess, H3.
You get a torsor over the, you get an R plus torsor over the moduli stack of surfaces.
And that, the cohomology of that is somewhat comprehensible.
The cohomology of an R plus torsor, I mean, this is a principal bundle over the moduli stack of Riemann surfaces. So I'm not sure what, I mean, if I have a principal, so you have the moduli stack of Riemann surfaces of genus G, and over it there is this thing D. So the fiber, if I have here, in here, the point sigma, then the fiber over this is D sigma, which is now a subset of this thing. So you want to take the cohomology of this with coefficients in sections of D?
I think my question is answered.
Okay.
D is classified by an element in the cohomology group of MG. And I was wondering,
with coefficients in the sheaf of smooth R plus valued functions, so that's 0.
No, you just pull back the cohomology class you wrote there, right?
yeah.
Maybe we can.
Anyway.
Well, I think you have now explained the title of your talk. Is that possible?
Maybe. Hopefully.
It's centroid.
Centroid, right?
Yeah, but there are many centroids.
Could I write this H3 as H2 of B of the cobordism category?
Yes, exactly. So if I was talking about just the cobordism category with like 1 and 2 manifolds, then I would write an H2. It's a thing that assigns, that takes one morphism and sends it to a torsor. And because I have 0, 1, 2, I boost it up to a 3. But yeah, that's right. That's the group that classifies section extensions. Yes.
Just one comment. I think you referred to Graham's definition of conformal field theory paper in the proposition, where the proposition was published. Which is published, that's what I'm...
No, I'm referring to something else, which is unpublished. I'm referring to a small...
Oh, something different.
A small thing called gluing Riemann surfaces together, which, if you're interested, I think Graham told me that I should feel free to distribute that. So it's like 4 pages long.
Okay. Oh, one more question.
I can ask later.
Okay. Let's thank Andrea again.